So well done for getting this far. This is just a short video to summarize what we've learned about vectors and their representations in different coordinate systems, and also how they transform between coordinate systems. So I'm going to write a single board that will summarize vectors, and we will be able to generalize then to tensors in the next video. Okay, so let's think about a vector. Let's call it t. And we saw that in one coordinate system, x1 to xn, this is some unbarred coordinate system, our vector t can be written as some components, t superscript I, times a natural basis vector, e subscript I. And we said these are called contravariant components, and these are natural basis vectors. And we also introduced different types of basis vectors called dual basis vectors. And we call these e superscript I. And to reconstruct our vector with our dual basis vectors, we need different components, t subscript I. And these are the covariant components of our vector. Okay, then we also thought about transforming from one coordinate system to another. x1 bar to xn bar. And here we can write the same relations, but we have different components and different natural basis vectors. Okay, and we have a bar on these to signify that they are in the barred coordinate system. And this equals contravariant times natural basis vector, or covariant times dual basis vector. Okay, so let me just... And then the next thing we looked at was how these all transform from the unbarred to the barred coordinates. So let's have basis vectors on the top and components on the bottom. Okay, and let's split our board into 4 quadrants. And here we will think about the natural basis vectors, here about the dual basis vectors, here about the contravariant components, and here about the covariant. Okay, so this is how I remember it. The contravariant components are these guys with the superscripts. And I always remember that a ti bar is equal to ti, so the components in the barred coordinate system equal the components in the unbarred system times some Jacobian dx by dx. And we have to think about where to put the bar on these and where to put the indices. Okay, and I've been silly. I've put an I here, and I know that I have to sum over this index, so I should call it something else other than I. So let's call it j. Okay, so I need to put an I and a j, either top or bottom here, and I need to put a bar somewhere here. So I remember it that for these contravariant components, if I start with t without a bar and want to end up with a bar, then I need to add this thing that has a bar on top. Okay, and that's just what we saw when we derived it properly with the chain rule. I need a superscript I, so this must be I, and I'm summing over j, which means I need one superscript and one subscript, so this must be j. Okay, and to make this clearer, let's remember that we can write dj is d by dxj. Okay, so this d by dxj involves a subscript. Okay, we'll come back to that in a second. So if you remember this, then you can get to any of the other quadrants. Okay, so I only remember this single piece of information. And the way to remember is that this thing is an element of the Jacobian matrix J bar. Okay, so if we start with covariant components T, and we change coordinate systems so that we go to T bar, the vector remains unchanged. So we know that the basis vectors must transform in the opposite way compared to the contravariant components. So we know how the natural basis vectors transform. If we have an EI natural basis vector, to get to the barred one, we must transform with the inverse of this guy. So we have a dx by a dx bar. And again, I've been silly and wrote I. Let's call this j. We have to sum over this index, so there needs to be a j here. And there's an I on the bottom, so this must be I. And this is the inverse of j bar, the matrix J. Okay, it's an element of J. So if you know this, then you know that the components and the natural basis vectors transform in the opposite way from each other. And actually, this is the origin of the name contravariant. This means against, so contra means against. And this is telling us that these components transform against how the natural basis vectors transform. So these guys transform with J, these transform in the opposite way with the J bar. Okay, so this is the contravariant components, the superscripts with the natural basis vectors. Let's now think about the dual basis vectors and the covariant components. And again, if you know this piece of information, then if you go this side, then we find that Ti, the set of covariant components, transforms from the unbarred system to the new barred system. And again, I've been silly, I keep writing i's. I know that I'll need to sum over this, so let's call it j. With some Jacobian matrix element dx by dx, and we need to put a bar, and we need to put an I and a j somewhere. Okay, so we know this, and if you remember that these guys transform inversely, or in the opposite way than the contravariant ones. So the covariant Ti transform with J. So there's a bar here, there is an I here, and there's a J here. Okay. And again, if you think about this as di bar x j t j, where di bar is equal to d by d x I bar. Then you'll see that you sum over one superscript and one subscript, and you have an index that's free, and that's I, and it's a subscript which matches with the free index on the left hand side. So this transforms with J, the Jacobian matrix J. So if we start at this point in this quadrant, if we go up, then we flip from J bar to J, and if we go this direction, we flip from J bar to J also. And the same thing happens as we go up this way, or from here to here. Okay, so instead of J, we're going to have a J bar here. Instead of J, we're going to have a J bar here. Okay, and you can go diagonally, but that confuses things. Okay, so the dual basis vectors are these things called EI. And we're going to think about what the barred one is in terms of the unbarred. And let's call this J. Okay. And as we said, we'll have a Jacobian matrix element, dx by dx. And it's going to be opposite, so it's going to be the J bar. So that has a bar on top. It has a J here, and it has an I here. Okay, and this when I write this, I'm really thinking about d, j, x bar I, e, j. So I know that the j superscript goes with the j subscript, and we have these free indices I on the left and right hand side. And this goes with the matrix j bar. Okay. So covariant means with, and these transform in the same way as the natural basis vectors with the same j. Okay, so these covariant and contravariant names stem from what the natural basis vectors do, and if they transform in the opposite way as the natural basis vectors, they're called contravariant. If they transform in the same way, they're called covariant. Okay, so hopefully that is clear. I would burn this into your mind. And as I said, you only need to remember one quadrant, and then you can get to the other quadrants. And we'll see that tensors are just generalizations where we have repeated matrix elements and repeated indices. So we'll come to that next. And just to say that these contravariant components, they're a set of n functions. So we've got n coordinates. I runs from 1 to n. And these are components that transform according to this, this rule. A set of n covariant components transforms like this. Okay, and when I write this shorthand, d by d x I equals d sub I, it's because this d by dxi is effectively a covariant function. Okay, so it is actually a covariant function. So if you write out the chain rule and see how this transforms, it transforms like this with a matrix element of j. Okay, so this shorthand is useful, and it's also rigorous and accurate. Okay, so now we move to tensors.